After completing the session 33 and creating text transcriptions from video, it is time to review this process and understand it better. So, what are we doing in our 33rd session? We are building a completely offline transcription engine. By using GPU acceleration, we will process speech up to 4 times faster than standard OpenAI Whisper models and organize it with absolute precision. We are taking a standard English video and pushing it through the engine to generate 3 distinct outputs: a standard text file, an SRT subtitle file, and a JSON data file. To build this, you need 4 things ready to go: an NVIDIA graphics card and a Conda installed on your system, FFmpeg active in your Windows path, and a short English test video. These 3 files function as the architectural bridge required to move from raw video into automated AI translation and dubbing. Step 1 is isolation. Open your Anaconda prompt and run conda create -n audio-asr and python equals 3.10 -y. Complex AI pipelines requires highly specific software versions. To prevent dependency collisions from breaking other modules, we need strict quarantine walls. Inside this secure audio ASR container, we install the PyTorch CUDA wheels and the faster Whisper stack driven by the Ctranslate2 backend. Before moving forward, run a quick Python script to check your CUDA device count. You need to see a 1 to confirm your graphics card is actually detected. If the terminal returns a 0 or throws missing DLL errors, your GPU is invisible to the software. You can fix this by either upgrading the Ctranslate2 package or using PIP to install the NVIDIA CUDA runtime libraries directly. Funneling the heavy lifting of speech recognition through the Ctranslate2 engine straight to a dedicated graphics card guarantees a massive processing speed advantage. Now we prepare the media file. We need to strip all the visual data away from our test video using FFmpeg. We use 3 specific flags here. -vn drops the video entirely, -ac1 forces the remaining audio into a single mono channel, and -ar16000 downsizes that audio samples to a 16 kHz frequency. Think of this as the AI's acoustic diet. Feeding a raw high-definition MP4 directly into a speech model wastes processing power on video decoding and causes VRAM memory crashes. The strict 16 kHz pre-processing step is not optional. It matches the exact acoustic format these algorithms were trained on, ensuring maximum accuracy while preventing hardware failure. Next, create your Python script and look closely at the model configuration variables. This chart shows how we map the model to your specific hardware. With a high-end card featuring 15 or 16 GB of VRAM, you can comfortably set the model size to large V3 and compute type to float 16 for production level quality. But if you are working on an 8 GB laptop GPU, the same setting will overflow your memory. You must step the model size down to small or medium and use int8 float 16 quantization to compress the data. You will see a parameter called VAT filter set to true, which stands for voice activity detection. When activated, VAT tells the AI to ignore pure silence and background noise. Without it, the Whisper model will often hallucinate or continuously loop the same text indefinitely during long pauses in the video. Run the script in your Anaconda prompt. you will see the system download the Whisper model into your cache, followed immediately by the real-time generation of timestamp text. By meticulously balancing model size and quantization against your exact hardware limit, we extract the highest possible transcription accuracy without triggering an out-of-memory crash. Go into your output transcripts directory to visually confirm the pipeline succeeded. You should see your 3 finished files. Open the SRT file. You will notice the industry standard sequential counters and arrow separated timestamps. This file is immediately ready to drop into any video editing software. Next, look at the JSON file. The structured dictionary array format here isn't meant for human reading. It is pure machine readable data designed for automated software. These time-stamped files are the foundational data required for phase 4. Next, an Indic Trans2 AI model will read this exact JSON file to begin the automated translation and dubbing process into Hindi, Telugu, Bengali, Kannada and all Indian languages.